When a fluid moves through a pipe that gets narrower, it speeds up. But where does that increase in kinetic energy come from? We've considered pressure, which can differ between two openings in a pipe. Fluids can also change height. The total mechanical energy of the moving fluid remains constant unless work is done by a net force, or pressure difference. So we have work plus mgy, which is the potential energy due to height off the ground, plus 1/2 mv squared, which is kinetic energy. That is going to be constant. Since we're dealing with a fluid, let's look at each term per unit volume. So we're going to divide each of these terms by capital V, volume. All right, so we have work divided by volume. We have mass divided by volume here and there. Remember, work is force times displacement. So if we immediately change work to be FD, all of a sudden we have displacement over volume. Let's take this derivation to the next slide. All right, so from the previous slide, we have force times displacement over volume. We had M over V, mass over volume, and we replaced that with rho because that's the definition of density. All right, so since the volume of water in the pipe equals this cross-sectional area A times this horizontal displacement D, what we can do is replace volume with area times displacement. Now we have D in the numerator and in the denominator. Cancel those out, and we get force over area. And we still have our gravitational and kinetic energies here. Force over area, by definition, is pressure. And here we have Bernoulli's equation, which is the main equation you will use when you are doing fluid dynamic problems. This right here remains constant as a fluid flows through a pipe. This equation comes in handy in any situation where you have a pipe that is changing shape and/or elevation. So here we have fluid flowing through a wide pipe and then it goes up and it gets narrower. In this sort of situation, you will be using Bernoulli's equation. One simple result of Bernoulli's equation is for horizontal fluid flow. As fluid speed increases, the pressure decreases. So here's Bernoulli's equation, and this is going to remain constant. And since the height is not changing, we're just going to get rid of that term because that's not going to change at all. And so you can see that as velocity increases, pressure will have to decrease in order for this whole amount to stay constant. And it is also very important to note that the continuity equation still holds true, even if there is a change in elevation. So sometimes you might have to use this equation here first to calculate a velocity so that you can then continue to use Bernoulli's equation. Here are some notes on problem solving with Bernoulli's equation. Number 1, the continuity equation A1V1 equals A2V2 holds true even if there is a change in elevation. For some problems, you will need to first solve for the second velocity using this equation and then use Bernoulli's equation. Number 2, when you are given a change in pipe radius or diameter, make sure you calculate the change in cross-sectional area using pi r squared. If the diameter doubles, you cannot simply double the area. For example, you can see here that r is squared in this equation because, the cross-sectional area of a pipe, it's a circle. You need to use pi r squared. Finally, if you are given a multiple choice question involving Bernoulli's equation on the AP Physics 2 test, it is advised to skip it and come back to it later, since these problems tend to take more time. Open the PhET simulation, Fluid Pressure and Flow, the Flow tab. So here it is. You can click on the Flow tab, and you see a pipe, and there's fluid flowing through it, and they have some dots to represent the molecules. You can use the speed here to see how fast it's going. You can check the pressure, and you can see you can have multiple pressure meters. You can see that deeper in the pipe has higher pressure since we're, more submerged. We're lower. So therefore, the weight of the fluid in the pipe above this point adds to the pressure. And we can increase the flow rate. So now there's, it's going to be moving faster. We can see what happens to a bunch of dots. Now that's not as interesting as what you can do here. We can lower the pipe. We can increase the height. You can actually use these to make it much wider so you can see that it slows down a lot, and then make it much thinner here, and you can see the fluid flows through real fast, right? And the pressure decreases a lot when the fluid moves faster. So this is a very fun simulation.